All right, in the last video, we talked about systems of equations and matrices and how you can solve them using a matrix. And basically, if you're given a system of equations, just like what we saw back in algebra, you can just abstract it and just take the coefficients and put it in a matrix, because a matrix is just an arbitrary collection of numbers. And then because we know how to do operations on this algebraically in order to solve it, we figured out there were 3 rules that we could use to mess around with this matrix and eventually solve the same equations, but in this kind of matrix form. And that's kind of helpful because it's easier to put into a computer and all that, but it's a little bit hard because there's no real visualization. It's just putting the numbers here and doing some algebraic manipulations with it. If you remember, systems of equations had this geometric interpretation of like lines crossing and where do they cross, or like planes crossing and where do they intersect. And so it would be cool if we had that sort of geometric intuition, but with our matrices. And that's where we kind of have this other layer of abstraction down here that I mentioned in the last video, where it's AX equals B. And so let's talk a little bit about each component here. A is a matrix, X is a vector, and B is a vector. In order to fully understand that, we're going to delve into what it means to multiply a matrix by a vector, or we're going to go through one interpretation. And that interpretation is going to be around changing the basis vectors in a space. And that will give us this really cool geometric intuition for some of our matrix systems of equations. So, in this picture, we just have our regular Cartesian coordinate plane where we have our basis vector, and I'll draw them in green here, of 1, 0 and 0, 1, right? You have your little I hat and your little j hat. And the question is, since you can define any vector on here with a collection of, or with some linear combination of these two basis vectors, for example, if I choose this point right here, right? You can see, and we know this right away, that's 2, 1, right? We call that point 2, 1. But what is that really saying? Well, that's saying that we go 2 times in the direction of I hat, so in the direction of the x-axis, plus 1 time in the direction of j hat, the y direction. It's like, okay, yeah, we knew that. But that's important because what if we change I hat and j hat, right? What happens then? Well, that's this picture. You can see that, let's just assume that this I hat's kind of in the same place. It's still at 1, 0. But you can see this j hat is different. Maybe instead of being, 0, 1, it's kind of over here at 1, 1. And it's weird to use coordinates because when I say 1, 1, I'm talking about 1, 1 in terms of these basis vectors, right? If you kind of overlaid this grid here, this point would be right around here, which is 1, 1. So now we have I hat as 1, 0 still. And instead of j hat being the normal 0, 1, we have it around 1, 1. So this point here, that was at 2, 1, let's say that we're still want to have 2 I hat plus 1 j hat. Well, what would that be? What would that be? Well, that would be 2 times in the direction of I hat. So this vector 1, 0, so 2 times 1, 0. And then 1 in the direction of j hat. And j hat now is 1, 1. And if you just do this kind of math here, you get 2 plus 1, 3, 1. So you see where before we had a vector at 2, 1, we now have a vector at 3, 1. So by changing the basis vectors, you can see how the whole entire plane is like squished in some way. And that changes pretty much every single vector on this plane is going to be transformed in some way. So for example, this one went from 2, 1 to 3, 1. An interesting question is which vectors were not changed, and that's actually an important question later on in linear algebra. And you might ask, why do we care about changing basis vectors? Well, one of the biggest applications is in computer science when you do rotations and things in like animations or visualizations or modeling, and you have a rotation, well, you can demonstrate a rotation as just a change of basis. And so let me flip here and show how we could do that. You have your traditional Cartesian coordinate plane like that, and you have your traditional I hat and j hat, which I'll just kind of show by doing these grid lines. Well, what happens if you rotate the whole thing, right? You rotate your whole coordinate system. So you'll see that the grid lines look the same. Because if you rotate all the grid lines, you have the same grid lines. But we have these different basis vectors, where our I hat now went from here to here. So our I hat is actually 0, 1. And again, I should probably be using bracket notation, because when I specify I hat, usually you're going to specify it as a vector. So I'll just put it here as a column vector. Now J hat went from there to there. It's now -1, 0. And so there's this way where you can describe this kind of change in basis using just where the two basis vectors end up. Now you might say, how can we put all this information together? Well, maybe you've already guessed, you can make a matrix. So let's make a 2 by 2 matrix where each column is a basis vector, and it tells us where the basis vectors end up after we do some transformation here. So for example, this transformation is a rotation, and we will by convention have the first column be I hat and the second column be J hat. And so we'll say, where does the I end up? 0, 1. And where does the J end up? -1, 0. And this matrix could be called a rotation matrix, but it describes this transformation. And to be specific, it describes this linear transformation. Remember, we're working with linear transformations in linear algebra. And what makes this a linear transformation? And what made this also a linear transformation? Well, every single one of the lines here, you can see remains a line. You can imagine there's some way to morph the plane in which somehow these lines get curvy. But if you only use the two linear operators that we talked about, which is scalar multiplication and vector addition, then any line in the plane, when you kind of morph the plane linearly, all the lines will remain lines. The angles between the lines might change like this, or the lines might rotate like this, but the lines themselves stay straight. And so that's kind of another way you can think about what does it mean to have a linear transformation. So anyway, back to what we were talking about. We have this matrix which describes a linear transformation. And you can imagine, and maybe you take a second to do it on this one, what is the matrix that describes this linear transformation? And you can pause or whatever. And we can think about, well, it's going to be a 2 by 2 matrix. We have, where does the I hat end up and where does the J hat end up? Well, the I hat doesn't change, so we have 1, 0. And the J hat, we said, we guessed it was about 1, 1. And so this matrix right here would describe this kind of skewing linear transformation. All right, so we have a new way to look at matrices now. Let's go back over here. We'll work with this matrix. We can view a matrix as where the columns tell us where the basis vectors end up after a linear transformation of the space. And you can start thinking about, what does this mean maybe in higher dimensions? What does a 3 by 3 matrix mean? Or even harder, what does a 2 by 3 matrix mean? But we'll come back to that later. For now, let's see what we can do with matrix vector multiplication and what that means in the context of this kind of linear transformation interpretation of a matrix. So we're going to come to let me use a better marker here, AX equals B. Focusing now on the fact that the left side is a matrix vector product, matrix A, vector X, and it gives you a vector. So the first thing you'll notice is that multiplying a matrix by a vector gives a vector. Now let's say that this is A here. A is our rotation matrix. A matrix vector multiplication can be thought of as basically what we did over here when we picked a vector and we said, oh, what happens to this vector when this linear transformation takes place? Well, we could see it kind of got stretched out over here and it ended up at 3, 1, where it started at 2, 1. That seemed like a random exercise, but that is essentially what AX equals B is talking about. Where X is some vector in the original space, the space here gets rotated. You can see that X will kind of end up right here, right? And the question is, where is that exactly? Well, by giving the multiplication of this matrix times this vector, we're going to define that as the resulting vector after the linear transformation. So let's think about mathematically how we might do that. Well, we know originally that this vector is 2, 1. So X we're going to call 2, 1. And I'm just going to bring A on over from where we figured it out earlier. What this means is that we have 2 times the I hat and 1 times the j hat in order to get our vector, right? That is true in the after picture. Even though I hat and j hat changed, it's still true that if you go 2 in the I hat and 1 in the j hat, we'll get our vector. So what that means is, in order to figure out this after vector, we just have to take 2 times I hat plus 1 times j hat. But we have to put in the new I hats and j hats. Where are the new I hats and j hats? Well, they're right here, right? The parts of our matrix. So what is this matrix vector product? Well, you're going to take 2 times the I hat plus 1 times the j hat. And you will see that that does give you a vector, right? Scalar multiplication and vector addition, again, are linear operators, not too surprising. This will give you -1, 2. And as you can kind of see visually, that is exactly where our vector will end up. Now you can imagine that in some more complicated linear transformation that maybe involves skewing the plane and rotating or some weird thing, that it would be really helpful to not have to kind of think through this, but just have a algebraic way to do matrix vector multiplication. And the way that works is you can kind of think of it as, let me make sure I get this right. All right, so let's try to get an algebraic definition for matrix vector multiplication. That way we can just have an easy way to calculate it, but just know this intuition is behind it, because this intuition of linear transformations will be super helpful when you're setting up the equation itself, and then you can just crunch the numbers using what I'm about to tell you. So in general, if you have an n by n matrix, and by n I just mean n is the number of rows and n is the number of columns, the vector has to be n tall. And of course it's going to have just a width of 1. The reason that this number n has to equal this number n is because n tells you how many basis vectors you need to define your vector. For example, this says 2 components, 2 and 1, because you had 2 times I hat and 1 times j hat. Those are 2 different basis vectors, I hat and j hat. Since you have 2 different basis vectors, you need 2 columns in your matrix to define where those basis vectors end up in order to tell you how your vector is changed through the linear transformation. So this n has to equal this n. Now, in our case, we'll just choose m and n to be 3 and n to be 3. So A, B, C, and again, this is generalizable to higher dimensions or whatever. And basically what you do is you take you're going to get a vector, right? It's going to be a 3-dimensional vector. You're going to take the dot product of this row with this column, and so you get AJ plus BK, right? You get the idea, you know, dot product. Then you take the dot product of this row with our vector. Then you take the dot product of this row with our vector. And again, that's just kind of a formula on how to do matrix vector multiplication, but if you look at our example here, you can kind of get some intuition on why we're taking the dot product, right? We're not taking the dot product out of nowhere. That's just how the math ends up. And that'll give us our matrix vector multiplication. Let's finish by returning to AX equals B and figuring out what all of this has to do with systems of equations. All right, I'm back to the front side of the board. We just talked about how if you have a transformation matrix A, and by transformation matrix it just tells you where the basis vectors end up, and you have some vector x, and you want to know before and after the transformation, maybe x is this black vector here, where it ends up, then you do a matrix vector multiplication and that tells you where it ends up. Maybe we'll call that B. So if this is known and this is unknown, all you have to do is matrix vector multiplication. But what if I gave you this black vector and you were trying to figure out what vector in the original space moved and became B, right? We'll call this B. And you're given the transformation matrix A, and you're trying to figure out what vector over here, well, we know it's 2, 1, but what vector over here came over and became this, where we said this was like 3, 1 or something like that. That's where we relate to our system of equations. Because now this is known and this is unknown, right? And so let's say that A, let's remember what it was here. I believe it was 1, 0, 1, 1 was our transformation matrix for this one. X is now unknown, so I'm just going to make this component x1 and this x2. So I don't know, they're just variables. And then we know B is something like 3, 1 or something like that is where it ends up. Let's just use our algebraic definition of matrix vector multiplication here. Remember, we take the dot product of this row with this column. That'll give x1 plus x2. And the dot product of this row with this column, 0 times x1 is just 0 plus x2. And we know this is going to equal 3, 1. And suddenly you start to see something that looks a lot like a system of equations, where you have the first component of this vector has to be the same component as this vector because these two vectors have to be equal. So you have x1 plus x2 equals 3, and then you have x2 equals 1. So very easy system of equations. You can figure out very quickly x2 is 1, x2 is 1, then x1 has to be 2, and we have our 2, 1. Boom, we solved what vector goes from here to here. You can imagine more complicated cases, you're going to end up with a really complicated system of equations. Long story short, any system of equations can be represented in this ax equals b form, where this x is unknown. That's why it's x, right? We use x for unknown variables. And b is some vector in the output space, and we're trying to figure out what vector, when multiplied by a, and remember multiplication means transformation, what vector when transformed by a becomes b. And it has this really cool geometric intuition of squishing or twisting space. And so next time we're going to figure out another way to solve ax equals b. Rather than turning it into a system of equations and then solving it, we'll figure out a way to do it just from a matrix point of view. All right.